webinar here from the Refeed Drive project, Control Strategies and Electric Drive Design. Refeed Drive is a project funded by the Commission in the Horizon 2020 framework program. The full title is Rare Earth Free E-Drives Featuring Low-Cost Manufacturing, which is exactly the key goal. So we want to avoid making use of rare earth permanent magnets in the motor core and develop a next generation of scalable electric drive chains. We are selected under the GV04, the Green Vehicle topic, together with some other projects. Runtime is 3 years, but of course, due to the delays and stop during the COVID-19 issues, we will ask for extension. So we hope to wrap up everything until March of next year, where you can expect the final results. Refeed Drive has 13 partners spread over 6 European countries. Today we will talk about power electronics and a little bit of design, also electronic design. So today we will hear speakers from University of Aquila and IFPEN in Nouvelles, but there are other partners involved in the different work packages you find on our website. Rare earth free, why is this so important? Because we have supply risk. The heavy rare earths, neodymium, dysprosium, are highly important, but also in supply limitations, very much concentrated. They are very costly compared to other materials, which raises the total motor cost. There is market uncertainty, price volatility, mainly due to Chinese strategies. And of course, there's some environmental and LCA issues with these materials used in the permanent magnet. Therefore, our ultimate goal is to avoid them, but not in the ivory tower. So the solution should industrial, feasible, should be possible for mass production, and ultimately have lower cost. We achieved this through clever material, to analyze the manufacturing process, design optimization, and scalability, which is also an important topic for today. As Fernando pointed out, there are two main motor technologies here: induction machine with copper rotor, both fabricated in die cast, and the synchronous reluctance machines, one with permanent magnet, but these are ferrites, so no critical materials, and one is a pure machine without any magnets. And important to understand our approach is that we have two power ranges, 75 kilowatt and 200 kilowatt, meaning 8 motors in total, with important key criteria requirements. We want to increase, based on the benchmark with the Tesla X60, we took as reference 30% more specific torque, 50% reduction of the direct motor losses, 15% less costs in mass production, and 50% increase of the power density in power electronics, and still remain scalable, meaning we have two power ranges, 200 kilowatt, which runs roughly until 800 volts, and a 75 kilowatt range, which runs between 350 and 400 volt battery level. But we will use in the power electronics, as well as in the housing and cooling, more or less the same components. And Giuseppe will speak later precisely on the wide bandgap silicon carbide semiconductor models. So scalability is the one very important issue. Achieved is the architecture solution, the design, the components, the mechanical integration, and now we're really completing the final steps of manufacturing and assembly, motor and power electronics to be tested, which has already started with the 75 kilowatt variant at IFPEN. Will then be tested also in other test benches, and ultimately we will put at least two motors in an LCV vehicle under drive cycle conditions, which hopefully will give us the test results by end of the year. This was just a quick flipping through. Please go to our website or to a cluster page in LinkedIn, where you can find more detailed information, reports, latest news, announcement, etc. And this is the second one of our webinar series, so there's more to come. As an appetizer, Next plan is to show.
Sorry for this technical issue. And with this presentation, this part of the tutorial, I'm going to provide few concepts and results of the power electronic design developed within the Refri Drive project. Just to understand this device, but considering the pool, everything manages this kind of things. Power electronics is has a central role in the electric powertrain for electric vehicles because it has to manage the full power of the motor, possibly at the maximum efficiency, and it is demanded to apply the commands coming from the user and to provide the maximum acceleration and brakings, preserving the life of the battery. So it is a very central component. The architecture, I'm sorry, and this component is mainly based on a control hardware that runs the motor control algorithms that you will receive details in the next presentation, and power hardware. In this presentation, we are focusing on the power hardware that is mainly based on a classical topology, meaning the three-phase inverter. The main components of this power converter are the solid-state switch that can be found in the market grouped as power electronic modules, DC capacitors, and voltage and current sensors. The main things is that this kind of switches are affected by conduction and commutation losses, as most of you may know. And one of the design issue is to select the most appropriate switching frequency of this power converter. The switching frequency depends on the motor electric parameters and on the maximum operating speed of the machine. In our project and in the real world, the tendency today is to increase the speed of the machine in attempting to enhance the power density of the motor and then save weight and size inside the electric vehicles. So increasing the speed of the machine, the feeding AC voltages tends to increase in the frequency. Just as example, in our motor design, we are going above 20,000 RPM, and with this kind of speed, the frequency of the fundamental voltages in our motor is in the range of 1,000 to 2,000 Hertz. Then the switching frequency of our power converter will arise up to 25 kilohertz, or this kind of frequency range, and the commutation losses of the power components will drastically increase, making difficulties to manage the component's temperature and to maintain it within acceptable values. So with this consideration, and considering the today most used switches that are IGBT and MOSFET, it's quite challenging to achieve these requirements with high power density power converter. So we started to take into account new technologies that are being introduced in the market. These technologies are based on wide bandgap semiconductors and are the silicon carbide power electronics and gallium nitride. While gallium nitride are mostly being introduced for low power application, silicon carbide technology seems very promising in the application of traction powertrain in electric vehicle. In particular, you can see in the figure left that the performance of the traditional silicon-based components are overcome by these new technologies. In particular, with silicon carbide technology, high voltage operation can be achieved, and the components can operate at higher temperature and with higher switching frequency. For these reasons, it is estimated that in the recent future, this kind of components will replace the traditional IGBT and MOSFET components in a lot of applications. So about these technologies, the cost is the main issue, and it affected the market penetration of the silicon carbide devices. But the latest studies and forecasts seems to be positive with this market penetration. In particular, the diffusion of these devices is driven by the high efficiency they present and the fact that they are able to extend the range in electric vehicles. Coming to refree drive project, considering the high efficiency, high power density target we have, and as I mentioned, the high speed of the machines, including also the fact that in our error-free design, the torque to the current ratio is reduced because we don't have powerful magnets to sustain the torque at low speed. We are somehow obliged to go in the direction of silicon carbides. Moreover, we must consider the scalability target that we want to maintain, and the fact that the commercial batteries are rated to 400 volts, and some application we have also availability for 800 volts batteries. Considering this, and considering that in our project only off-the-shelf components are available because we have no partnership with foundry or power modules integrator, the choice was oriented to available components rated 600 volt or 1.2 thousand volt. But you can see that in the market, the lower voltage ratings for silicon carbide is not present with high current ratings, but you can find modules up to 100 amps. Some OEM, meaning Tesla, Tesla is using silicon carbide technology in the Model 3, but they are using parallelized modules, introducing inefficiencies in the design. We look at also on the IGBT side, but we found that looking at weight and size, the packages are very close to the silicon carbide modules for the high voltage rating. So, considering also that we have two different power settings to satisfy the 200 kilowatt and the 75 kilowatt with different performances, we think to obtain scalability, changing the voltage of the batteries. So at the end, the same power module was used for the whole power range. I like to remind that these two power ratings are the extreme boundaries of the power range. We like to demonstrate the scalability of the power converter. The selected power modules was the best in class available on the market, and comes from Mitsubishi. It is rated 1.2 thousand volt of blocking voltage and 800 amps of collector current. The module performs very good in our evaluation, even because it has a very thick copper base plate that assure a good thermal capabilities of the modules. In the graph on the right, you can see how are the efficiency capabilities of this module compared with the best-in-class IGBT we was evaluating as a counterpart. For this module, we are able to estimate that in few years, the cost for mass production would allow $3 per kilowatt power electronics. Other design characteristics of our power electronics was the presence of the laminated DC bus bars, because considering the very fast switching characteristics of the silicon carbide technology, a reduced parasitic inductance on the DC bus side must be assured. So in cooperation with Mersen, we completely designed from scratch the laminated bus bar. And to assure the lowest inductance possible on the DC bus side, we also included thin film capacitors. These kind of capacitors are also useful to enhance the power density of the power converter. Just some view of the prototypes. You can see on the top left of the slide the bus bars manufactured with integrated capacitors and the full assembled power electronics. Also pictures of the complete housing integrated with the motor cooling is presented, and the whole project was developed in cooperation with R13 Technology, IFP Energy Nouvelles, and Nouvelles Powertrain for the design of the housing and liquid cooling. So few results of our design. We reported some key performance indicator. For the 200 kilowatt power setting, we hope to reach, tests are in progress, but from our data, we are reaching up to 20 kilowatt per kilo of specific power, and same values for the kilowatt per liter power density. Efficiency in both cases is up to 98%. And as I said, the power electronic cost is in the order of $3 per kilowatt. The lower power setting is a bit penalized, but because essentially of the power module packages we found it in the market, but the adoption of the 1.2 thousand volt power components provide a little better efficiency in the powertrain, in the power converter. Thank you for the attention.
Marco Tursini from the University of L'Aquila. I am professor of electrical machine and drives, and I am pleased to present in this webinar an outline of the issues related to the control of synchronous reluctance and induction motors developed under the RefriDrive project at the University of L'Aquila. Both synchronous reluctance and induction motors are controlled according to the principle of field orientation in an equivalent two-phase reference frame, usually denoted as DQ frame. In case of the synchronous reluctance motor, the DQ frame is fixed with the rotor and aligned with the minimum reluctance position. The torque depends on the product of the DQ current and the motor magnetic anisotropy. That means the difference between the D and Q axis inductances. For the induction motor, the DQ frame is oriented with the rotor flux linkage and the torque depends on the stator Q current and the rotor flux. This last depends by the DQ current through a first-order dynamic system affected by the rotor time constant delay. The slip speed, in turn, depends on the Q stator current divided by the flux. The field-oriented current control of the synchronous reluctant motors is shown in this slide. It requires two current regulators for the DQ currents, Park transformation for the input currents, and Clark transformation providing the output voltage command. Then a space vector pulse width modulation algorithm is used to compute the logic commands of the three-phase inverter branches. A decoupling algorithm can be included to linearize the control dynamics among the two axes, D and Q. This algorithm depends on the motor inductance really, that are saturation dependent, and this is a critical task of the control scheme. Control optimization is designed considering two basic trajectories in the DQ currents plane: the maximum torque per ampere and the maximum torque per flux, which is equivalent to maximum torque per speed, really. In the constant torque region, that means below the base speed of the motor, the MTPA is assumed, which is independent on the motor speed. Above the base speed, the control region is restricted by the voltage supply limit. Speed-dependent transition towards the MTPF curve is a practical choice for optimizing. Of course, actual machine saturation and current limits must be accounted in control design. This slide shows the implementation of the optimum control strategy of the synchronous motor. Basically, we need a control module which has the torque command and the speed as inputs, and the DQ current references as output toward the field-oriented current control. The optimum control trajectories are generally implemented by lookup tables due to the nonlinear machine behavior. The figure shows the curves computed for the 75 kilowatt motor developed inside this project. In case of the induction motor, the field-oriented current control has the same structure of the synchronous reluctance motor, apart for two elements: a rotor flux estimator, which is fundamental because from it depends the correct field orientation, and an outer flux loop, here implemented in terms of rotor magnetizing current, which is simply proportional to the rotor flux. A basic estimation method refers to the rotor flux current model, but more sophisticated approaches can be used, such as state observers. Anyway, all of these methods depend on the motor parameters. And this is a critical point of the induction motor control, which could require further adaptation techniques. Optimum control of the induction motor can be designed by using the same approach of the synchronous reluctance motor in the DQ current plane. But in this case, the D current is replaced by the rotor magnetizing current. This means that the delay in torque production due to the rotor time constant is neglecting in designing the control strategy. The figure shows the curves computed for the 200 kilowatt motor developed inside the refried project. The MTPA design curve has been found to match practically the maximum efficiency trajectory, although this must be still confirmed by tests on the motor prototype. The optimum control of the induction motor can be arranged looking at possible driving scenarios of traction vehicles. High dynamic operation, such as in sport mode, could require constant rotor flux operation, while maximum efficiencies, such as desired in cruise or eco driving modes, are achieved on the MTPA curve. The transition between these curves must be also implemented. And high-speed operation requires to approach the MTPF trajectory, while a minimum flux value is desirable to allow for safe field-oriented operation. Then the optimum control scheme is similar to that of the synchronous reluctance motor, which a module that has the torque command and the rotor flux speed as inputs, and the magnetizing and Q current references as output. The control trajectory can be implemented by lookup table as well in order to account for non-linearity such as saturation issues at high currents. This slide shows a simulation result which refers to the 200 kilowatt induction motor and show the dynamic performance during the startup, which is supposed to happen in sport mode, and the following activation of the cruise mode when the motor has reached the steady state speed of 6,000 RPM with a load of about 100 Newton meters. We can see and quantify the transient delay between the D current and the flux magnetizing current due to the rotor time constant. The control of both the synchronous reluctance and induction motors is implemented on one of the last generation floating point microcontroller unit produced by the Texas Instruments. And the software is implemented by using MATLAB Simulink support. The figure you see in this slide shows the top level of the control model in Simulink. The software architecture is basically an idle loop interrupted by control and communication routines. Some of them, such as the serial communication routines in this scheme, are implemented for development and debugging purposes and will not appear in the final software release, replaced by CAN communication function. The control interrupt is synchronized with the PWM carrier and the end of ADC conversion of the motor currents. The PWM and the sampling time of the controller is 50 microseconds that correspond to 20 kilohertz. Currents and DC voltage are inputs from the 16 bits ADC converter and 12 bits resolver position. The resolver is used both for the synchronous reluctance and induction motors. This information is input from the serial peripheral interface at each control period. The software implementation in Simulink is really the direct mirror of the control schemes we have seen in the previous slide. Each control module, PI controller, Park-Clark transformation, and so on, is implemented in MATLAB language by using embedded MATLAB function connected each other by the respective input and outputs. The Simulink embedded coder support for Texas Instrument processors allows the direct generation of the control C code from Simulink. This environment assures very fast prototyping of the code and code efficiency as well. Preliminary tests are going on since the beginning of Jan in our lab at University of L'Aquila, starting with the 75 kilowatt synchronous reluctance motor. The tests are intended for bearings run-up at no load condition of the motor prototypes and the setup of the drive, sensor measures, and control software. This slide shows some of these tests, basically related to check the reliability and the speed range capability of the drive system. All data are required through the serial communication interface by an host console running in Simulink. These are all experimental results. Finally, to close my presentation, and thanks you, I want to show a video reporting one of these tests. Thank you to all.
Good afternoon, everyone. Hope you can hear me correctly here. Just a very quick background on me. I'm a control engineer. I've been a control engineer for 10 years now. I started 10 years ago with the internal combustion engines as well, then as hybrid systems. And I've been dealing with electric motors for a little more than 5 years now. I'm now responsible of electric motor control works at IFPEN, IFPE Energy Nouvelles. My presentation, I hope, is complementary to the very interesting one of Marco Torsini that shows in more details control algorithms. I will try to focus more on our controls workflow as a whole, and how do we proceed actually to make a motor work, very simply. IFPEN controls a workflow that aims to develop and validate control algorithms. As one simple objective is to ensure that the process is seamless, that we can go easily from pre-design to experimental validation. It's based on what we call a tool chain, which has four main components. The first one is control-oriented models of motors and inverters, which are 0D dynamic models. Also, we have the capability of running dynamic time-based simulation of the control algorithms we develop that we couple to those models. As the same as was shown by Marco Torsini before, we use then automatic code generation of those control algorithms. And we have an extended capabilities of fast prototyping and data logging tools to help us, in the end, accelerate the experimental characterization of prototypes and the development of control algorithms. To summarize, I will try to kind of show how this works more specifically. This tool chain has the objective to create bridges between our, I would say, 4 work environments. There's the pre-design, in which you have simulation data, for example, from finite elements. And we use that simulation data to make analysis, look for optimal operating points, stuff like that. Then you have the time-based control simulation with the controls algorithms and the dynamic models. Of course, there's the test bench where you can check everything for real, and you get some data that you need to analyze. The tool chain, mainly, there are 2 main uses in between upstream analysis and controls time-based simulation, which are help and automate the creation of zero-D dynamic models. And also it's a support for algorithm design and pre-calibration. Then, as discussed before, you have, of course, the automatic code generation to go from controls time-based simulation to the test bench. And it's important to have the possibility to acquire some control variables and data. I'm not referring here to bench acquisition, but only to control signals. We have also a watt meter and some other instrumentation to measure phenomena. And of course, the main goal here is to get feedback from this data analysis, so you can make better pre-design, better control simulation, and better test on the test bench. It all starts. This workflow we apply. We'll try to share with you our process in a little bit more details in the following slides. We applied it on the refried drive project for both 75 and 200 kilowatts permanent magnet assisted synchronous reluctance motors. I will try to illustrate that. It all starts with the finite element simulation. We compute the results, and we can store those results into maps, which can be 2 or 3D, depending. We can take into account the position of the mechanical position of the motor, for example. Then using the dynamic electrical equations and, for example, Hamiltonian or Lagrangian modeling approaches, we reach a 0D dynamic model of the motor that takes into account, for example, magnetic saturation and, if needed, rotation harmonics. We can also use this data we created, of course, to build the maps that were mentioned before by Marco Terzini in his presentation, which are optimal operating points. We can account for DC voltage losses, motor resistance, the variation of modulation index, and also, for example, end winding leakages. I've illustrated here the max performance for the 75 kilowatt motor in blue, and also some characteristic operating lines, like in red, the start of the flux weakening area. Once you have your model, you can take your control algorithm, put that into a Simulink. You have here on the middle, on the right, an illustration of the root level of our Simulink controls. And you can use that in a time-based dynamic simulation, for example, to pre-tune the field control you want to use, or develop, for example, and validate new algorithms. We also have the possibility to use inverter models and also mechanical modeling. Once this code is validated, we get to the automatic code generation. Our code generation is also based on the MATLAB Simulink code generation, but we added several capabilities that is associated to our basic software and inverters. For example, we can directly from the simulation environment choose for which inverter it is, what the hardware configuration of the inverter, or for example, choose the list of active control parameters we want directly from the simulation environment. Also, logging selection data, logging data selection is made straight here. The basics software with which the generated code, sorry, is then interfaced is fully developed in-house, which allows us to implement the techniques and the controls we want at the lower level. For example, specific modulation techniques or live variable frequency, anything you want to try. The code is then, of course, downloaded in our inverters, and you have here in the middle, on the bottom, the HP range inverter that we tested on our benches with the 75 kilowatt motor here as an illustration. So we can now move to actual experimental testing and analysis with this inverter and the motor on the test bench. So far. And I think a good proof of the efficiency here of our controls workflow is that it allowed us to perform the needed testing on the bench in 10 days time slot with the mounting on the bench and everything included, which is we are quite glad of that. And of course, also it's not limited to these types of motors, and if needed, we can use it again and adapt it for other types of motor. So this concludes my presentation, and I hope I maintained you a little bit interested. Thank you for listening.